Hello and welcome back to Calculus 3. We are continuing our chapter 12 exploration, section 12.2 on graphs and level curves. I wish the title had also functions of several variables in the title, because this is the first lecture on functions of several variables, and this is where we define a function of several variables, which will pretty much be the same as the definition you guys had for a function of a single variable from pre-calculus. The function of several variables means that you have more than one independent variable that will contribute to the outcome of the whole function. So if you say, okay, I would like to know what is the weather like today. The temperature, air pressure, humidity, well, all of these different concepts put together create what the weather is like at the moment. So temperature T is a variable, humidity H is a variable, air pressure P is the variable, and whatever, the wind, the direction, and all of these kind of things. So you have a whole bunch of things. Each one of those is a separate independent variable because air pressure and temperature have nothing in common, right? So each independent variable contributes to the global picture. So far, what you had in your R2 world is y equals f of x, and you had x and y axis. X was your domain, y was your range, the output, and you had only those two dimensions, x and a y. Now, yesterday already we had equations which were like z equals, let's say, what was it? X squared over a squared plus y squared over b squared, and you had this kind of thing, right? Which was the elliptical paraboloid. So if you look over here, you still have the input side, and the input side would be x and a y, and you would have the output side, which is z. So this is what we would call a function of several variables, because you have more than one input. You have input x and y. So we are talking about multivariable functions in terms that you have more than one variable in your input, in your domain. So now we have to start with the definition of the function of several variable. First, before I write this, I will just remind you that of the definition from pre-calc for a 2D case. It says a function is a rule which assigns to each x in a domain a unique y in the range. One more time. A function is a rule which assigns to each x from the domain a unique y in the range. So now it should make sense just to upgrade this and say a function is a rule which assigns to each point from the domain a unique z in the range. So you have the ordered pair xy, which is your input, and then you have a single z in the range, which is your output. So definition is, say, a function z equals f of x, y. I'll just say is a rule. I'm changing a little bit what they have, which assigns to each point xy in the domain a unique z in the range. So this is the So this would be a 3D case, right? Because you only have x, y, and z. Can you modify this for higher dimensions? Sure. W is a function of x, y, and z, which assigns to each point, which is now a 3D point, x, y, z, a unique w in the range. Are we going to have that in this class? Yes. Because when you look at the object of any kind, you can talk about its density or you can talk about its temperature, and that would be the fourth dimension, because this is already a three-dimensional object, right? This would be, you can either say, okay, it's approximately a sphere or elliptical paraboloid, like a watermelon, right? So whatever you want to call it, it is a three-dimensional object that is fully explained by x, y, and z coordinates. Well, as soon as I bring in a fourth concept as density or acidity or temperature or whatever you want to add to this, right? That fourth concept will be the fourth dimension. So I can say the temperature of this object, it depends on the location, right? And then you give an equation of the object and which way the temperature will propagate through the object or whatever. So, what is the 4-dimensional space, 10-dimensional space? It's just a number of variables that you have to consider as you are thinking about any concept. You know, when someone says, oh, space-time, it's x, y, z, and t, time, right? You add the time because you deal with space-time all the time, right? The exam today was at, we started at 10:50, so exam was at 10:50 in this classroom. This classroom has its 3D coordinates in the universe, right? You can set your coordinate system 0, 0, 0 somewhere, and in respect to that 0, 0, 0, this classroom has a unique XYZ location, and then you just say, okay, 10:50 on July 19th, 2018, you pinpoint the time, that's the t variable, and you have your x, y, and z. There are your 4 variables. It's a 4-dimensional, right, entity, so we say space-time. And then you can go through anything. Just take a 3-dimensional object and say, okay, the density, heat, or whatever else. So now, when you are looking at this definition for 2D, 3D, 4D, it doesn't matter. What we always have is going to be, we have some kind of domain that maps into some kind of range. Now, for R2, you had a number from x-axis map into a number on the y-axis, and that was what f of x used to do. Now, in R3, you have a number that it's a point in xy, so x0, y0, and that is going to map into some z0 on the z-axis. So your domain used to be 1-dimensional, which corresponded to 1-dimensional output. Now you have a 2-dimensional input going into the 1-dimensional output. This concept is extremely simple. I will give you z equals 3x squared minus y, and then I will pick point in a domain, let's say 1 and 6, and then you will say, okay, z equals 3 times 1 squared minus 6 is equal to -3. So z equals -3, which means, all of this means that 1, 6 produced -3, and you have the order triplet in 3D that is 1, 6, -3. If I give you an equation of a sphere, right, and I give you x and a y, you will be able to calculate z value, and the z value will be on the top of the sphere. So that's all this is. So when I give you a function, whatever that function is, it's going to be a function. So I can involve trig, I can involve logs, and I can involve exponential. Anything goes that you learn, square roots and absolute value, everything. No matter what this is, as long as you know what your input is, you should be able to calculate output just by doing the arithmetic, right? Computation. Is that a question? Or no?
Yeah, I was just wondering. I thought that's at time with the fourth dimension is not. It just can be, right?
As I said, you don't think of dimension as a length. It could be length, but dimension is just a fancy word for a variable. So if you are calculating the body mass index, right, BMI, they want to know your age, they want to know your height, they want to know whatever the parameters are, right? There's no length. Yeah, well, actually, height is length, but the age is not length, right? So whatever, if anyone Googles the formula for BMI, you'll see, or anyone, if anyone knows what goes into that calculation, body mass index. I know that age and height are two of the variables. So when we say dimension, we don't necessarily mean just distances like x, y, z. Dimensions on, as I said, that's the reason why I talked about the weather, right? We never, yes?
The formula for BMI is just weight in kilograms over height in meters squared.
Oh, I thought there was a third thing in there as well. Because I taught a math course a few years back, and there were three different things. All right, well, thank you. So, can you please repeat the BMI formula for body mass index?
Weight in kilograms over height in meters squared.
So weight in kilograms, the height in meters. Or it was going to be meters squared. What happened?
BMI says like I'm close to being obese.
BMI said you were close to be obese? Nice.
I'm like a 28 on the scale. It's like very overweight.
The way to quickly test that is just if you have access to the Wii Fit, you know, the balance board they have. Yeah, you step on it, it says you're too fat to play, you know. I went around that because if I sit on a couch and just put my legs on it, it thinks it's a 3-year-old on the board. So I can play as a 3-year-old, and I just destroy the whole game. It's say okay, anything you want. You just need to do a little bit of pressure. So it has its pluses, you know. So BMI formula would have two-dimensional input. Guys, I can rebrand this formula as z equals x over y squared, right? There you go. This is the same thing. Mathematical abstraction here, and its application in the what you call a real life, because over here is a fake life. So, right? Is this fake? Good. So that is that. So now we would like to know, right, the story of the domain, the story of range. We would also like to see what these level curves do for us. So domain is set of all possible input points. Note that you are not allowed to use values that would give you negative number within ln or negative number under the square root, you know, or some of those things, or a zero in denominator. So all of the rules that you learned for domain from your pre-calculus course, they stay in place. We don't learn new tricks. We just take the tricks that we know and we adopt them now for our 3D functions. So in in your previous life, so in R2, right, you had a function f of x is equal to square root of x plus 3. And the question was, what is domain? Well, the way you would solve that, you would say, I am only allowed to plug in non-negative numbers. So you would say, okay, make this non-negative. This is the way you make it non-negative. It has to be positive or 0. So when you solve this inequality, you get x larger equal than -3, and this is your domain. So any number -3 or bigger, you are allowed to plug into that function, and you will get an answer. So if you are using, let's say, 6, then 6 plus 3 is 9, square root of 9 is 3. If you are using, let's say, -2, 3 plus -2 is +1, square root of +1 is 1. So you are not allowed to use any numbers smaller than -3. So that's what the domain is for. Domain is there to tell us the set of values that you are, right? So now, WeBoard, right, we already mentioned. What is the domain? Domain for the WeBoard is up to 250 pounds, right? Which is why I can't play. So if you are more than 250, well, tough luck, right? Now in R3, your function f of xy, which is z, is going to be maybe given as, let's say, square root of 2x plus y, right? So this is what it's given as a function, and we are looking for domain. Well, please note that all of this over here is just going to end up being a single number that you are going to square root. So if the trick before was that one thing under the radical needs to be non-negative, well, the same trick must work now. There are no exceptions in mathematics. So 2x plus y still must be bigger or equal to 0. Now, when you solve this, you no longer get just a set of numbers. You actually now get a set of equations which cuts off a region. Now, that makes sense because your domain is no longer a number line. Your domain now is xy plane. And xy plane cuts off regions. So, if you solve this, you will see that y, it needs to be bigger than -2x. Now, what does this mean? So this is your answer. This is your domain. Now, if you graph that domain, as you will need to later on in chapter 13 and so on, if you graph this as a function, you see that your x-intercept is 0, and your slope is -2. So we are talking about a line like this, okay? And your y needs to be bigger than this, so you will either shade to the left or you will shade to the right. You need to know which one to shade, which is the reason why you actually did these problems in your algebra courses. So now you can pick a test point, you know, like 1, 0, and plug that in, see if it works. If you pick point 1, 0, I mean, there are many ways in which you can do. Picking a point in one of the regions and checking that in your inequality is the safest and fastest way to do it. So you plug in 1, 0, you get that 0 is bigger than -2, which is a correct statement. So you will be shading over the point that gave you correct statement. So this is your domain, right? This is the test point. So this is your domain. Your domain are all of the points that are in the shaded region. Now you can go and you can pick anything. Anything you pick in a shaded region will work in the original problem. Anything that you pick from the region you haven't shaded is not going to work because it's going to give you a negative number. You can test that. See, -1, -1. is in the corner over here, in a third quadrant. And if you plug in -1, you will have a square root of -3. Square root of -3 is not a real number; it's imaginary. So you can't have -1 and -1 as the input for this particular function. Now, with some tweaks, obviously, you could make -1 to be the input. So all of the tricks which you learned before for domain remain the same. If you have some kind of a division, right, a rational function with x's and y's, say you have x squared divided by y minus 3x plus 5, well, you need to make sure that this is not equal to 0, right? Those are the things that, so anything that you have learned, I want to actually go and pick up some of the homework problems. I just made up these square root things. I want to see what else is there in the homework that you are supposed to consider for the domain, and then we'll go from there. So let me see. Function defined. What is the domain of? Perfect. Right. So problem number 2 is asking you for the domain of the function x squared y minus xy squared. Well, that's a polynomial. And what do we know about polynomials? Right, in 2D, all real numbers, then in 3D must be all of R2. Right, so anything goes. Now, problem number 3 says f of x is equal to 1 over xy. Aha! 1 over xy. So, in this case, right, it's a rational function. So now, we know that xy cannot be 0, which implies that x is not allowed to be 0, and y is not allowed to be 0. Guys, these are lines. So domain for this problem is everything but x and y axis. So axes are the only thing that are excluded, because axes, which obviously include the origin, axes contain zeros, and when if you pick a point on the axis 3, 0, well, your y is 0, and that makes denominator 0. If you pick any point on the y-axis, like let's say 0, -5, well, then your x is 0, and you still get 0 in the function on the denominator, which you are not allowed to have, because we can't divide by 0. It's not you can't divide by 0, it makes no sense to divide by 0, because division is making piles, right? So if I have 2 objects and I want to divide this by 2, I'm creating 2 piles, and each pile gets assigned 1 object, right? So that's what the division is. If you have a pile of stuff and you want to divide that pile of stuff, you can divide this pile of stuff by 2. So you create 2 piles, and then the third object gets cut in half, and each one goes into each, so you get 1.5 in each pile. You can have a pile of stuff and divide into 3, right? Which is dividing into 3 piles. What makes no sense is to have a pile of stuff and divide that into 0 piles. How are you going to do that? Can you take this and divide into 0 piles? Right? You can't, because you are starting with having 1 pile. And if you divide this by 2, you're creating 2 piles, and you put stuff into those 2 piles. So it's technically like you walk out of a store, you have a bag of stuff, and then it's too heavy, you think bag is going to break. What do? You get another bag and you divide. That's dividing by 2, right? You're taking a full pile of stuff, you divide into 2 bags, and now that's divided by 2. Would it make sense to walk in with a heavy bag out of whatever store and divide your one bag into no bags. You have a bag of oranges that it's too heavy, and then you just say, okay, yeah, I'm going to divide this by 0 now, which means no bags. You just kick them home, right? One by one. So, actually, when I think better, I can divide this into 0 piles quickly. I've been working on that mathematical concept and that definition since the beginning of the class. I don't know if you guys have noticed, but yeah. Anyway, yes?
Well, I know, like, technically this isn't the case, but sort of conceptually, dividing by 0 is kind of like results in infinity.
That would be in the concept of a limit. You are correct, but that's in the limit. When you divide by 0, it goes to infinity, but physically can be done.
Right.
All right, so let's. What are you're gonna love this one. All right, so here's the one for you to practice, and then we'll talk about the other concept, and we're done. Find the domain of g of x, y, defined as ln x squared minus y. All right, so the rule for ln is that you are only allowed to plug in positive numbers. So no 0 allowed, no negatives allowed. So we have to deal with x squared minus y larger than 0, strictly. That's it. So we set the argument to be larger than 0, and then we solve this inequality. I'm just going to move y to the other side, getting x squared larger than y, and then say y less than x squared. So if y is less than x squared, I can draw the parabola and then shade either inside or outside. So which one do I shade? What do you think? Inside or the outside? We need y to be smaller than x squared. Well, you can test 0.20. That's definitely below x squared graph. If you test this, you plug in 0 for y and 2 squared, right? 2 for x, 0 less than 4, that's a true statement. Therefore, we are shading, oops, I have to shade this way. So we are shading everything on the outside. That's what we are doing. So we are shading everything on the outside and then this inner piece. So now you can also check real quick. You pick 0, 3. If you pick 0, 3, you see that 3 is less than 0, and that's not good, right? So to solve these types of problems, right, you quickly employ whatever you learned in your pre-calculus to figure out the domain. So denominator can't be 0, or argument is bigger or smaller, and stuff like that. The last part is to talk about level curves. So level curves are horizontal cuts of the function. So you get level curves as you assign z values to be z equals 0, z equal 1, z equal 2, right? So you have some kind of discrete values for z, and then those discrete values for z will give you cuts through the object. So if I have a good old elliptical paraboloid, which we've seen many times, z-axis, as you can see, the lowest value over here is origin 0, 0, 0. So it makes no sense to have z negative in this case. Any other cut that you make, so this is a cut at 1, this is a cut at 2, this is a cut at 4, and let's say this is a cut at 5. So when you look at these, right, we cut this function, right, which could be object again, right, because that's what we are dealing with. We have objects. When you cut it with parallel planes, which are all z equals planes, right, parallel to x-axis, you are getting some kind of 2D functions. What you do is you squish those functions onto domain. And if I draw the domain, now we are looking at this top view. What I'm going to have in this case is this one. Then I have this one, and then this one, and then this one. See that? So that would correspond to these. Let's see one of these in a textbook. Well, let's take a look at a few of these in a textbook on page 878. What you have is a sheet of paper that it's bent and put at an angle. So now when I have that, I cut with horizontal planes through it, and I get these kinds of parabolic shapes. And those are called level curves. Now, those level curves, which are green on the picture, are clearly visible over here. So you see that there is a slope to walk over here. Now, that slope, as you can see, that slope is not as steep as the slope of the sides. Remember that this is a parabola on the side, so that these slopes on sides are very, very steep, right? Where the slope, when you look at it this way, is not as steep. So it's very easy to walk up and down this way, not so easy to walk up and down on these sides. Now, that is exactly what level curves show. If you look over here, the slope where the vertices are, right? These vertices are separated, and these guys are really close together. So these level curves show that when the level curves are closely packed, when they're dense, it shows that a very steep change in vertical in height, where when they are separated, it's not as much of a slope. This thing helps us greatly to develop terrain maps. So if you have seen maps, you've probably seen all of these really busy lines, right? What these really busy lines are level curves. So now, if you are in the military, and you know they don't drive on roads, they just drive through forests and fields and mountains and things, right? You look at the map, right? And you look at the map, and you know that when this is happening over here, and all of this, well, that's like this, and you're not going to drive on those kind of slopes. When you're here, yeah, you're good to go, right? Your vehicles are going to go anywhere, off-road vehicles. So this over here, not too much of a slope. Level curves are far apart. This stuff over here, well, that's all like this. So level curves are very, very helpful. Now, they could be used, not just to show the vertical distances. We can use them for fields and other things. The electrical potential function is given here. So you can think of this as termite nests. And if you take a look at the termite nests, you don't see too much of a slope and a rise in these areas. And you can see that the level curves are far apart for all of these small ones. But as soon as you go up the tube, it's like this, and look what happens to the level curves. They're very densely packed. Do we see that? Now, it's very important to make these cuts on the regular interval, right? So whatever your delta z is, you have to keep that delta z. You can't make a cut of 2 feet and then a cut of 1 foot and then a cut of a half a foot, right? That doesn't make sense, because your level curves are not going to show what they're supposed to show. So as you are doing these cuts, they have to be at regular intervals, and then you let the slope and the shape of the object govern how far these level curves, because that's what level curves are supposed to detect, right? How steep of a slope you have to beat in order to go up or down on the shape. You simply calculate these by plugging in values, z equals 0, z equals 1, in the equation, and you are getting other equations. So this is a very quick last example. If I have a watermelon, right? So this is a watermelon, and this watermelon sits on a table at a single point, and the equation for this watermelon is, let's say, x squared over 9 plus y squared over, so that's going to be this way, over 100 plus.
Might want to swap the screens.
Z, I don't, but since you want it, z minus 4 squared over 16 equals to 1. So this could be a watermelon sitting on the top of the desk, and you can see z minus 4 because it's 4 up, right? That's 4 feet. These are hey, yeah. It's my size watermelon, all right? If you look at this, all I need to do to find level curves is to say, okay, z equals 0, z equals 1. And as I am placing different z's into equation, I will be getting ellipses, right? Because every time I put a z equals a number, it eliminates this. And you just get an ellipse after an ellipse after an ellipse, and they're all going to be concentric. So go with z equals 0, z equals 1, z equals 2, z equals 3, and so on. And what you are going to get is a point, and then an ellipse, an ellipse, an ellipse. And then they're actually going to go to the, when the watermelon is the fattest, which is the equator, right? And then they're going to go and shrink back into a point. And then if you use a z that you are not allowed to use because you went over the watermelon, you're going to start getting nonsense, right? Because you will not be able to compute things. And those will not be any more equations of the ellipse. Tomorrow, 12.3, 12.4, we are. I tried. I tried. Fine, Monday. So we'll try to work out through chapter 12. So 12.3 and 12.4. Remember that your labs, guys, we already covered 2 sections, right? And your next 2 labs are for the next exam. So labs 2 and 3. So when do you start your lab 2? Yeah, exactly, today. What else are you going to do? It's really bad outside. Look at that. It's sunny.